Hello everyone, this is Dr. Webb and welcome to this abstract algebra video. In this video we are going to introduce something that is really central to the study of ring theory, and this is what are called ideals. So let's jump right in. So an ideal is a special type of subring. So given a ring R, we're not assuming anything about R except for right now just that it's a ring, then we call a subring I a left ideal if for any time that we take something in R and something in R, which we're calling R, and some X in the ideal, then we have that R times X is also inside the ideal. So X times anything else in R is going to land inside the ideal. So we call it a left ideal if R is being multiplied to the left of X. If it happens when R is multiplied to the right of X, then we call it a right ideal. So when R is a commutative ring, which is when most of our focus is going to be on right now, then this distinction between left and right ideals is lost because multiplication is commutative. And so these left and right ideals are the same thing. And so in that case, when we're in a commutative ring, or in general, if we have something that's both a left and a right ideal, we call it a two-sided ideal, or just an ideal. So what are some examples of ideals? And we're going to be sticking, for the most part, with commutative rings here. So the set 0 by itself, that is the trivial ideal. That is always an ideal. And the entire ring is an ideal. If you multiply two things in the ring together, you land back in the ring. That's one of the necessities of being a ring. If you take something in the ring, then we can talk about the ideal generated by that. So if we have A is in R, then the ideal generated by A is all the things in the ring times A. So R times A for all R in R. And if you notice, we use the same notation here as we do for cyclic groups generated by A. And so that's kind of the way you should think about these principally these ideals, these principal ideals, these ideals generated by a single element. They're similar to cyclic ideals, cyclic groups, subgroups that we learned about in group theory. For any integer n, then the principal ideal generated by n, which often we would write as nz, but we could also write this as the ideal generated by n. So this is a principal ideal of the integers. And so, 6z is all the multiples of 6, 2z is all the even numbers, etc., etc. And so the important thing about ideals is what makes them stronger than just a subring is this fact that in a subring it just has to be closed under multiplication. But for an ideal, it has to be closed where you take anything in the ideal, multiply it by anything else in the ring, right? And so how do you tell something is an ideal? Well, first, it has to be a additive subgroup. That's part of being a ring, and so this is just the one-step subgroup test. For addition. So same as because a ring is a special type of, because an ideal is a special type of subring, then it has to be a subgroup for addition. And then the second step, the second thing you need to prove is really just part of the definition of being an ideal, is that A times R has to be in the ring for any A in the ideal and any R in the ring. And so if you were doing this for the difference between this and a subring is for a subring, all you need is for this R here, AR to be in a if both A and R are in A. And so loosening the restriction on R, saying that R can be anything in the ring, this is a much stronger requirement on ideals. Okay, and so even though this is listed as a theorem, there really is nothing to prove here. Wrapped up in this is both the definition for subring and an ideal. And so the theorem the statement of the theorem pretty much proves it. Okay, so subrings versus ideals. And so really you should think about subrings as being subgroups, being like subgroups in group theory. Then in that case, ideals would be really kind of playing the role of normal subgroups, right? So if this was an SAT question, it would be sort of subrings is to subgroups as ideals are to normal subgroups. What do I mean by that? Well, as we've been saying, every ideal is a subring. So the even numbers, this is the principal ideal generated by 2 in the integers. This is going to be an ideal of the integers. But not every subring is an ideal. So for example, the integers are a subring of the rational numbers, but it is not an ideal of the rational numbers because, say I could do 1/3 times 7. This is not in the integers, even though 7 is in the integers. And so this is showing that the integers is not an ideal for the rational numbers. And so the big point of an ideal is that if you have an ideal and then you take anything else in the ring and multiply it to things in the ideal, you always land back in the ideal. Okay, and this is the big difference between ideals and subrings. This is the added part of the definition. Okay, so for ideals, we can talk about cosets of them. And this is kind of leading into how ideals are like normal subgroups. So ideals are additive subgroups of a ring, just like all subrings are, but ideals in particular we're focusing on here. So ideals are additive subgroups of a ring, and so we can use that to talk about the cosets. And so if I is an ideal in R, and we take any R in R, then we can talk about the coset associated to R, as we'll write it as R plus I, and so this is R plus all the things in the ideal. Okay, and we're using this notation, and this is following along with how we would talk about cosets for an additive group. And so this notation mirrors the notation for cosets of an additive group. And oftentimes, rather than having to write out R plus I all the time, often if I'm talking about the coset corresponding to R, I'll talk about R bar. And so remember that cosets, this is an equivalence relation. This does form an equivalence relation. On the elements of R, in that if everything is inside its own coset, if R bar, if R is in S bar and S is in T bar, then R is in T bar, and vice versa. If R is in S bar, then S is in R bar, etc., etc. Okay, and so now that we have these cosets, we can talk about coset arithmetic between them. And this is really what gets us, and this is what makes ideals special, and this is what makes them similar to normal subgroups when we're talking about cosets. And so let R be a ring, and I be an ideal. Then for any S and T in R, we're going to let S prime be in the coset generated by S, so S plus I, and T bar, or T prime is going to be in the coset generated by T. Then s prime plus t prime is going to be in the coset s plus t, and s prime t prime multiplied together is going to be in the coset coming from st. So we're going to call s plus I, we're going to call that s prime, and t plus I, we're going to call that t prime for right now. And so since s prime is in s plus I, this means s prime is equal to s plus I1 for some I1 in I. And similarly, t prime we can write as t plus I2 for some I2 in I. And so then if we have s prime plus t prime, this is equal to s plus I1 plus t plus I2. And then since addition is commutative, we can rearrange this any way we want. And we end up with s plus t plus I1 plus I2. And so I1 and I2 are both in I, and so their sum is in I because it is part of being an ideal is being in an additive subgroup. And so overall, this is inside s plus t plus I, and multiplication we can think about similarly. So s prime times t prime is going to be s plus I1 times t plus I2. And then if we FOIL this out, we get st plus I2 plus t I1 plus I1 I2. And the important thing on the right is s times I2. Well, I2 is in I, and so anything times it is going to be in I. Similarly, t times I1. I1's in I, so anything multiplied it is inside I, and then two things inside I are obviously inside I. And so we have st plus three things in the ideal. The three things in the ideal added together are in the ideal, and so this is in st plus I, the coset corresponding to st. And it's this right here, this attribute right here, which is really is the important part. It shows the important part of the ideal. Being able to take anything, s times anything in the ideal, and saying that that's in the ideal, that's what makes this work. And so this definition is really necessary for this coset multiplication with, for this coset multiplication arithmetic to work properly. So we absolutely have to have this definition for it to work. And so what this means is that if we take a ring and an ideal, well, we can do the same arithmetic with the cosets that we can with the ring in general. So these cosets themselves form another ring, which we're going to call the factor ring or the quotient ring, very similar to how when we had a group, we had a normal subgroup, then the cosets coming from the normal subgroup, they form another ring, the G mod n, the quotient ring in that case. And so, again, using sort of our shortened notation, this s plus I, you think about as being s prime, t plus I being t prime, and you get what you expect. S plus t prime, s plus t bar. So s prime, or s bar times t bar gives us st bar. And so this is, the arithmetic works out exactly as we want, because we take anything in s bar plus anything in t bar, we're going to land in s plus t bar. If we take anything in s bar and multiply it to anything in t bar, we're going to get something that's in s times t bar. And so So in this quotient ring, the coset generated by I is going to be 0 bar. So 0 is inside because I is an ideal. It's a subring, so it has 0, so 0 is inside of it. And so this is going to be our identity of the quotient ring. Because I is an additive subgroup and in addition, this is a commutative ring. And so this ard mod I, this is a quotient group in that sense. And so that means that it is a group under addition because I is a normal additive subgroup. And then for the multiplication, all we need to do is prove that it's closed, but we proved that in the theorem. And so that establishes. And all the other properties of a ring are inherited from R itself. So the associativity, the distributive property, all of that is going to work out just fine. So there's really nothing to prove beyond this. Okay, so this is, if you need to take a break, this is a good spot to pause. We're about halfway through the material in this. And we're going to be moving on to some special types of ideals after this. So I'm going to pause for a couple seconds. Okay, now we're going to talk about two special types of ideals. So first is what is called a prime ideal, and the ideal prime should make you think about prime numbers in the integers. And the definition is set up to mirror that. So if we're given a commutative ring R, in fact, for the rest of this, we're only going to be thinking about commutative rings. We want our I to be a proper ideal, so it is not equal to the entire ring. Then we're going to say that it is a prime ideal if for any two times, any time that we have two elements in the ring, and when you multiply them together, you end up inside of I, then one of them had to be inside of I to begin with, right? And so this is similar to, you should think about prime ideals. This definition was really coming from, one important way to think about prime numbers, and where we say that in prime ideals, we say that I is prime if for any A and B in R with AB being inside I, that implies that A is inside I and or B is inside I. So how is this mirrored over in the prime numbers? Well, we say that P is prime in the integers. One way to define primeness is if for any n and m in the integers, if P divides n times m, then P divides n and or P divides m. And so this P dividing n times m, this corresponds to A times B being inside the ideal. So P dividing the product is the same as the product being inside the ideal. And then the conclusion that, again, being inside the ideal is mirrored to the prime dividing it. Okay, so as we were just saying, one prime example of prime ideals is ideals of the integers generated by a prime. So n times z is a prime ideal if and only if n is prime. And so this is straightforward. Just coming from the definition, this shows that if n is prime, in what we just showed in the last slide, if n is prime, then you have a prime ideal, because having k be inside pz, well, this is the same thing as saying that p divides k, because pz is all the multiples of p. That's really what the definition of PZ is. On the other hand, if n is composite, this means there exists L and K that are bigger than 1 and less than n, assuming that n is positive, such that L times K is equal to n, and so then this would mean that L times K is inside of NZ, but neither L nor K are inside Z, because they're not big enough and can't divide. L nor K cannot be inside NZ, because neither of them are divided by n, divisible by n. So if you look at Z mod IZ, so even though the ideal generated by 2 in the integers is prime, this is no longer true for if you add in the imaginary number I with Z, because you can do 1 plus I times 1 minus I. If you work that out, you're going to get that that's equal to 2. And so neither of these are inside the ideal generated by 2. And so this is not in 2, and this is also not in 2. And so there's a product of two things in this ring, Z adjoin I, that give you 2, but neither of them are. So this means 2 can't be prime in this ring. So 0 is going to be a prime ideal of a commutative ring with unity if and only if R is an integral domain, right? And so remember, R being an integral domain, this means R has no zero divisors. And so if R has no zero divisors, and you have, so if R is in an integral domain, then, well, the ideal generated by 0 is just 0, and so AB multiplied together equals 0 if and only if A equals 0 or B equals 0. On the other hand, kind of taking the contrapositive, is if R is a commutative ring with unity, and if R is not an integral domain, well, being an integral domain means that there are no zero divisors, and so not being an integral domain means that there is zero divisors, and so R has zero divisors. Let's call them C and D. When you multiply them together, you get 0, with C not equal to 0 and D not equal to 0. And so then this means that C and D, neither of them are inside the ideal generated by 0. because the ideal generated by 0 is just 0. Okay, another type of ideal that's important is what's called a maximal ideal. And so what makes an ideal I maximal is it has to be a proper ideal, still similar to prime ideals. And if you take, there's any ideal that I is a subset of, but that is a subset of R, so you can kind of think about this ideal J as being in between I and R, then the only possibilities is that J is I or J is R. And so really there are no other proper ideals that I is contained in. So this definition is saying, i.e., there are no other proper ideals of R that contain I, that I is a subset of. So this is where the maximality comes from. This is sort of the biggest proper ideal that you can get. The biggest in the sense that it can't be a subset of any other proper ideal. Okay, so what does it really mean to be a maximal ideal? Well, we say that I is a maximal ideal if and only if you try and take something that's not an I, and then you look at this I plus the ideal generated by A. And so what this is shorthand notation for is this is talking about I plus all the multiples of A, where I is in I and R is in the ring. And so this I is coming from I, and then RA is going to be coming from the principal ideal generated by A. And so when you look at this set of everything in the ideal, anything in the ideal plus any multiple of A, you end up with the whole ring. So everything in the ring can be written like this, as I plus, as some element in the ideal I plus some multiple of A. So in particular, that means that if R is a commutative ring with unity, that means that that there exists some R in the ring and some I in the ideal such that R times A plus I equals 1, equals the multiplicative identity. And so this is our multiple of A plus something in the ideal, gives us this set is going to contain everything in the ring, and one thing that's in the ring is the multiplicative identity. And so this is an important fact. This is a very useful thing to remember that you can do if you have a maximal ideal I, that you are able to do this. And so how do these prime ideals and maximal ideals interact with each other? Well, if we're talking about our ring being the integers, then the prime ideals and the maximal ideals coincide with each other. So any prime ideal is maximal in the integers, and any maximal ideal is prime in the integers. If we look at the polynomials over the integers, the ideal generated by x is prime, right? If you have any element, if you have f of x times g of x are inside the ideal of x, that means you can write it as x times f of x times g of x would have to equal h of x times x for some h of x. And what that means, and so this implies that at least one of f and g don't have a constant, can't have a constant. Because if they both can't have a non-zero constant term. Because if they both had non-zero constant terms, then their product would have a non-zero constant term. And so it wouldn't be, you couldn't factor an x out of all of it. And so if whichever one that's true for, then you can factor an f out of that. And so let's just assume that f has no constant. Since f is a polynomial with no constant, that means you can factor an x out. And so that would mean that f is in the ideal generated by x. Okay, and so that shows that that it is maximal, or that it is prime. It is not maximal because if you look at the ideal, and so this is a bit of notation, if I do the 2 comma x, so this is talking about, this is equal to R2 plus SX, where R and S are both in here. This is a proper ideal inside the polynomials, polynomials with integer coefficients, but it is larger than the ideal generated by x. And so this is a proper ideal. So what I'm saying exactly is that the ideal generated by x is inside this ideal and not equal, and this is inside and not equal to that. In fact, in this case, this ideal here is maximal and prime. It is possible in some rings for you to have a maximal ideal that is not prime. And so, for example, if our ring is just the even integers, then the multiples of 4 is a maximal ideal in there. There's no proper ideal that's going to contain all the multiples of 4 that isn't all the even numbers. But it is not a prime ideal because 2 times 2 is inside 4z, but neither of them is a multiple of 4. But 2 is not in 4z. And so that's showing that it's not prime. And so in that last case, it was important that we are starting off with a ring that doesn't contain a multiplicative identity. And so we were able to do that because 2z, because the even numbers, it is a ring, but it's not in a ring with unity. If we had a ring with unity and we take a maximal ideal, then we are guaranteed that it has to be prime. And so the idea is suppose, let's take 2 elements in the ring with A and B being inside R, or being inside I, where I is maximal. And we want to show that this means that I has to be prime. So let's just say that A is not inside of I. Because if A is inside of I, then that would fit the definition of prime. If A is not inside of I, then we're going to show that I is prime by showing that B has to be inside of I then. And so if A is not inside of I, by what we talked about with maximal ideals before, and this being a ring with unity, this means that there exists some R in R and I in I, such that the multiplicative identity 1 is equal to AR plus I. And now what I'm going to do this whole thing is multiply both sides by B. And so we have that B is equal to AB times R plus BI. I can stick B in the middle there because we are in a commutative ring. And so AB is inside I. That's what we said at the beginning. So R times something in I, that's going to land us inside of I. Plus B, we're multiplying to something in I, and so by definition of an ideal, that's automatically inside of I. And so no matter what, we're adding together two things in I, so B has to be an I. So if we have AB lands us inside our ideal, and A is not in the ideal, then B had to be in there. Okay, and so this shows that I is prime. And so having this multiplicative identity allows us to get this equation right here, and that gets us going for this proof. Okay, so the important part of being a prime ideal is that then if you look at the quotient ring associated to it, then you're going to be guaranteed to end up with an integral domain. So I think this is a proof that we can do bidirectionally all at the same time. And so R mod I is an integral domain. Well, this happens if and only if for any S bar and T bar, so we're using the bars notation to talk about the cosets in R mod I, S bar, T bar equals 0 bar if and only if S bar equals 0 bar or T bar equals 0 bar. So without loss of generality, I'm going to assume that S bar equals 0 bar. And so this happens, S bar is equal to 0 bar if and only if S is inside of the ideal. Whenever S times T is inside the ideal. And so then this happens. This is the same as saying that I is prime. Okay. And so this really does go backwards. So R mod I is an integral domain if and only if whenever we have two things multiplying together equaling the 0 in that quotient ring, then one of them had to be equal to 0 in the quotient ring to begin with. And so this is the same as saying that one of them had to be in the ideal, because that's what it means to be in 0. I mean, that's what it means to be equal to 0 in the quotient ring whenever the product is inside the ideal. And that's the definition of being prime. Going backwards, if I is prime, then that means that one of them, either S or T, maybe I should say that, or T is inside I whenever their product is inside I. And so this happens if and only if in the quotient ring, when you have two things multiply together to be 0 in the quotient ring, one of them had to be 0 to begin with. And so then that corresponds with R mod I being an integral domain. Done. Okay, so then what does it mean to be maximal with, what does that mean for the quotient ring if I is maximal? Well, more than just being an integral domain, it means that R mod I is a field. So it means that every element is every element in the quotient ring has every non-zero element in the quotient ring is a unit, has a multiplicative inverse. Okay, and so remember, this is important that we're doing this with unity. And so I think in this one I'm going to start with I is maximal. And since we're dealing with a commutative ring with unity, we can use the fact that we used before. So this happens if and only if for any A that's not in the ideal, there exists some little r inside of there such that 1 is equal to A times R plus I for some I and I. And so that means in particular that if we move now to think about what's going on in the quotient ring, this means that for any A bar, which is not equal to 0 bar, there exists some R bar in R mod I, such that 1 bar is equal to A bar times R bar. And since 1 is the multiplicative identity in R, 1 bar, this has to be the multiplicative identity in the quotient ring, because of this follows straight from the coset arithmetic theorem that we proved earlier, because 1 doesn't change anything, and so multiplying by the coset connected to 1, multiplying by 1 bar is not going to change anything in the quotient group, and so this implies that A bar, that let's make this right. So for any A bar not equal to 0 bar, then we have that A bar is a unit because it has a multiplicative inverse, and this is what it means for R mod I to be a field. And so let's run through this argument both directions just to see how it goes. So if I is a maximal ideal, that happens if and only if we take anything in the ring that's not inside the ideal, then there exists some R, and this R should not be in the ideal. This R should be in R. So we are doing some correcting on the fly. So I being maximal implies that if we take anything that's not in the ideal, then there exists some element of the ring R such that the multiplicative identity 1 is equal to A times R plus something in the ideal. So again, that's what it means for I to be maximal in a commutative ring with unity. And so then this happens if and only if, so if A is not an I, that means that A bar is not inside of I, so it's not equivalent to 0. It's not in the equivalence class of 0, so A bar is not equal to 0 bar. And then R is going to be some equivalence class, so that turns into R bar in R mod I, such that 1 bar plus A bar times R bar. And so the I goes away because I bar, since I is an I, R bar is equal to 0 bar. And so that's why I goes away right there. And then for all A bar not equal to 0 bar, that means that A bar is a unit. And so this is what it means for R mod I to be a field. Going back the other way, R mod I is a field if and only if everything that's non-zero is a unit. That means if to be a unit, then it has a multiplicative inverse. That's what R bar is. If it has a multiplicative inverse in the quotient ring, that means that that 1 is in the coset of A times R. And so to be in the coset, that means that A times R plus some element in the ideal I is equal to 1. And if this is true for any A that's not in the ideal, then that's what it means for the ideal to be maximal. Because you can't include, there's no proper ideal bigger than it. If you try to add anything else into it, you're going to get the whole ring. Whew. Okay, so those are two very important theorems, and that's an important way. It's an important way to tell if a ideal is prime or maximal. So remember, prime ideals correspond to quotient groups that are integral domains, so don't have zero divisors, and maximal ideals, these correspond to quotient rings that are in fact fields. And so that's the important takeaway to this. And again, this is all working when we're working with commutative rings with unity. And so this is one of the reasons why we like commutative rings with unity. That is all for this video. I will see you again soon.